All right, today we're tackling a coordinate system that's, absolutely essential for engineers and physicists, but it can be a real headache. Spherical coordinates. But stick with me, and in just a few minutes, you're not just going to get the concept, you'll be ready to use it. For real. Let's do this.
Seriously, just think about that for a second. You could say it's, X miles east, Y miles north, and Z miles high. But doesn't that just feel kind of clunky? You're using a system made for boxes to describe something that is, moving in a giant circle.
And that's really the heart of the problem, isn't it? Our good old Cartesian system, X, Y, and Z, is awesome for things with flat sides and sharp corners. But the moment your problem involves spheres, think a planet's gravity, or how an antenna radiates a signal, using that boxy system just makes the math a nightmare.
So here's how we're going to break it down. First, we'll see exactly why boxes and spheres don't mix. Then, I'm going to give you this great analogy, your own personal GPS that'll make the whole thing just click. After that, we'll hit the math you need, walk through an actual example, I'll point out a super common mistake, and we'll wrap it all up with your brand new spherical toolkit. Okay, let's dive into our first section. Look, the biggest lesson in any technical field is learning to use the right tool for the job. And believe me, coordinate systems are tools.
We all know and love X, Y, and Z. They're comfortable, but trying to force them onto a problem that has natural spherical symmetry, wow, you're just creating so much extra work for yourself. Describing a simple sphere in Cartesian is messy. In spherical coordinates, it's beautiful. It's simple. It's all about finding the path of least resistance.
Now this is the part that's going to make it all make sense. We're going to build a mental model here, an analogy that you will not forget. We're turning these abstract variables into your own personal targeting system.
So, forget X, Y, and Z for a minute. Our new coordinates are r, theta, and phi. So what do these targeting parameters actually tell us? Let's break it down. First up is r, and it's the easy one. It's just the straight line distance from where you start, the origin, directly to your target. Think of it as the range. How far away is it? That's your r. Simple.
Okay, next is theta. Now you really got to pay attention to this one. It's the angle measured down from the positive z-axis. Let's call the z-axis the North Pole. So theta is your declination angle. If you're aiming straight up at the pole, theta is 0. If you're aiming straight out at the equator, theta is 90 degrees. All the way down to the South Pole, that's 180 degrees.
And last but not least, we have phi. This is your rotation angle around the z-axis, just like longitude lines on a globe. It starts on the positive x-axis and just sweeps around the equator. This is your rotation. So you see, you set your range, then your declination, then your rotation, and you can pinpoint any location in 3D space.
Okay, let's actually build a point right now. Imagine you're standing at the origin. What's the very first thing you do? You figure out your range. You point a line of length r straight towards your target, P.
All right, now we set our declination. We just take that line, that r, and we tilt it down from that vertical z-axis by whatever our angle theta is. See? We're getting closer.
And here's the final move. We take that tilted line and we just swing it. We rotate it around the z-axis by the angle phi. And boom, we have landed exactly on our point P. Range, declination, rotation. That's all there is to it.
Okay, so the idea makes sense. It's intuitive. But how do we actually, do the math? This next part is like a Rosetta Stone. It gives us the formulas to translate between the language of boxes and the language of spheres.
And here they are. These 6 formulas are all you need. On the left, you can see how we go from Cartesian to spherical. Notice that r is basically just the 3D Pythagorean theorem. And on the right, you see how we go back. It's all about using some basic trick, sines and cosines, to project our spherical point back onto the x, y, and z axes. These are your translators.
Theory is one thing, but let's get our hands dirty. We're going to take a totally normal Cartesian point, P 1, 3, 5, and we are going to convert it into spherical coordinates using those formulas we just saw. Okay, let's do this step by step. First, range, r. We plug our numbers into the distance formula. 1 squared plus 3 squared plus 5 squared, that gives us the square root of 35, which is about 5.916. Easy. Next, declination, theta. We plug in our values, do the math, and we get about 32.31 degrees. And finally, rotation, phi. That's just the inverse tangent of y over x, so 3 over 1, which gives us 71.56 degrees. So there it is. Our point is now 5.916, 32.31 degrees, 71.56 degrees. Done.
All right, listen up, because this next part is super important. I'm about to show you the #1 mistake that trips everybody up when they start using spherical coordinates. If you can avoid this trap, you are going to save yourself so many headaches.
So think back to our GPS analogy. The rotation angle, phi, it makes sense that it goes all the way around, right? A full 360 degrees or 2 pi radians. So does our declination angle theta also need to go a full 360 degrees to be able to point everywhere?
And the answer is a huge, emphatic no. This is the trap. The only valid range for theta is from 0 to 180 degrees. That's 0 to pi radians. Anything outside that is just wrong. But why?
And this visual explains it perfectly. Think about it. If you just sweep theta from the North Pole, which is 0 degrees, straight down to the South Pole at 180 degrees, and at every single one of those declination angles, you let phi do its full 360-degree rotation, well, you've already covered the entire surface of the sphere. You've painted the whole thing. If theta went any further, you'd just be pointing to places you can already get to. It would be redundant.
All right, let's bring it all together. In just these last few minutes, you've picked up a really powerful new set of tools for looking at the world.
So, let's do a quick recap. 1. You have that intuitive GPS model. Range, declination, rotation. That's your mental anchor. 2. You have the 6 formulas you need to convert back and forth. That's your translator. And 3, you now know all about the theta trap, and that theta only goes from 0 to pi.
And that's a wrap. You now have a way more elegant, way more efficient way to tackle problems that have that spherical shape. So the only question left is, what are you going to use it on first? The choice is all yours. Thanks for watching.